All right, let me see. Oh yeah, okay. Kevin, Bailey, are you out there? Sean, there you are. There. Huh?
760 is integration into tables.
Yeah,
So it's the table. No, but it's the table. 760. The approximate integration.
Trapezoid or
All right, guys. So I want to go over one type in section 7-8. One type of integral we didn't talk about yet. Then I got a handout for section 7-8 that kind of explains both types of integrals that 7-8 talks about. So the two types of integrals section in 7-8. The one we talked about already is when the interval that I'm integrating over is itself infinite, right? So if I integrate from 2 to infinity, our natural reaction to that might be, well, that's going to go to infinity if you add up something for infinitely long. But as we saw, there are examples where it doesn't add up to infinity. It's small enough, like adding 0.1 to 0.01 to 0.001, it actually comes out to a finite number. So something similar happens. So if I did that with 1 over x from 1 to infinity, the funky thing about this is it would actually add up, it would diverge, it would go to infinity. You guys with me so far? So if I did that with 1 over x, if I integrated from 1 to infinity, this would diverge. Let's go ahead and show that. Let's go ahead and do this problem together. So if I want to integrate 1 to infinity, 1 over x, what do I have to do officially? What must I do to handle that infinite limit? Yeah, I kind of gave it away there. The limit. So limit as t goes to infinity. T is kind of our go-to replacement variable, right? It's like our go-to limit variable. So now I can rewrite this as this. Because to be honest, integrals have to be, in order to do an integral with the definitions we've learned, it has to be over a finite interval, and it can't go to infinity anywhere inside the interval. That's the second type of integral that we've got to look at. So to take care of it, if I let this happen, then this is finite. It goes up to t. It doesn't go to infinity, it goes to t. And t is going to infinity, but it's not infinity. Are you guys kind of with me? And that's what limits do. Limits let us approach something, or we don't get there, so this is now completely legal. So don't skip this step, right? You have to rewrite this as a limit to officially be able to do it. And then, of course, what's the integral of 1 over x? Yeah, and why do I not have to worry about absolute value? Because I'm on the positive side of things. Cool, so I don't need absolute value. It's positive already. Is that cool? You can put it there, but you don't need it. From 1 to t. So the limit as t goes infinity of what? ln t minus ln1, which is 0. Kick ass. And of course, what does ln do as its input goes to infinity?
Smaller, smaller. Infinity. Biggest, larger. Bigger.
Bigger, bigger. It goes to infinity, right? So that's divergence. That's like I said. This area here is just too big. If you add it up forever, it actually does go to infinity. You guys with me? So that would be divergent. Goes to infinity. Divergent. So what's really kind of neat, at least to me, and I'm hoping to a few of you guys, is if I, instead of integrating 1 over x, if I can integrate 1 over x squared. So you guys try to do what we just did, but this time do for 1 over x squared. And just to help you out a little bit, nobody better end up with any natural logs. So try to do that the same way we just did that. Yeah.
The last term would be arrow or equals to infinity.
Well, I never like saying equal to infinity because that's a very strange statement to make. You can't be equal to a process, right? Infinity is not a number; it's a process. Divergent, exactly. Not the movie. I have no idea what that movie's like, but I'm going to stay away from it because it feels Twilight. Right? It's to create a new adjective. It's a Twilight out there.
We have to use T.
You don't have to. But it's sort of like not using y and x when you're writing a line. Right? You don't have to, but it's just the standard way of doing it. So my claim is this is going to be convergent, not divergent. You should come up with a number answer.
Why?
Oh, I kind of want to keep it there. So this is 1 over x. When I do 1 over x squared, can somebody tell me visually what would be the difference with 1 over x squared and 1 over x? 1 over x squared, how would it be different from this? So 1 over x at 2, it's at 1/2. 1 over x squared at 2, it's at 1/4. So visually, when I draw 1 over x squared in blue, it should be below this one, right? Because at 2, this is at 1/2, but this is at 1/4. You guys kind of with me? That's why, if I make that area a little bit smaller, it's smaller forever. It's just enough for it to actually converge. It doesn't diverge. It becomes a finite integral. So it's the fact that there's a difference in area to begin with that kind of extends forever that made the purple line, this guy, diverge. If I push it down a little bit, suddenly it's convergent. Does that help you do any problems? No, just the idea behind the problem that we're doing. It's why some integrals are convergent and some are divergent that go to infinity. Okay. So what happens if I do this? Bring the limit in. So what do I get when I integrate that? Good, so negative 1 over x from 1 to t. So that would be limit t goes to infinity of negative 1 over t plus 1. The gas, and of course this goes to 0, so whoever said 1, exactly right. Kind of freaky. Thank you. All right. Yeah, at least you can humor me and just pretend like it's cool. So it's really neat that it actually, to tell you honestly, any power greater than 1. So if I would have put a 1.1 power there, and what I really mean is less than negative 1. Are you with me? So if I have something in the form 1 over x to the p, if p is greater than 1, this will be convergent, the integral of this. And if p is less than 1, this will be convergent. If p is less than 1, divergent. Less than or equal to 1, sorry. Kind of neat. Obviously, if p is a negative power, it's actually like integrating x squared or something, and that's going to obviously go to infinity if you add that up to infinity. That's with me? Of course, that word obviously is a risky one to throw around, but that shouldn't be too freaky. Okay, so the other kind of thing that can happen, so that's how we handle it if one of the limits themselves is infinity. What do I do if it's the integrand, the expression on the inside, is infinite somewhere? So for example, if I had, get in there. So of course what happens here? Exactly. So as it goes to 5, it's going to be 0 on the bottom, which means the whole thing's going to go to infinity. Right. 1 over 0 goes to infinity as I approach 0 on the bottom. So from 3 to 5, at 3, this is 1 over square root of 2, which is whatever the hell it is, 0.7. And at 4, it's 1. And so here there's this asymptote here, right? So it's kind of neat. Let me give myself some more room here. So what we saw earlier was 1 over x squared was low enough that this area didn't go to infinity when I added it up over and over. 1 over x was too high. You guys semi with me. 1 over x was up here. It was too much. It actually went to infinity. Maybe. So what's really neat is if I have a vertical asymptote, like I do here, it's going to slam up like that. So if this is too wide or narrow enough, it's going to converge or diverge. It's the same thing. You just do this. Same thing. Okay. Zero reaction. Okay. So what do you think I have to do with this to be by the book, to be careful?
Limits.
I have to do a limit. And actually I have to be very careful how I do it. I can't just say this. Let me see if somebody can pick up why. And what's wrong with what I just wrote? It's a little tiny thing wrong. Really easy to not realize that you have to be careful. No, it's okay. So the problem is what's the domain of this guy? What's the largest x value I can plug in there? 5, right? So I can't approach 5 in general because that by means you approach it from both sides. I have to only approach it from below, right? So I got to go to 5 from below. A little tiny thing that if you don't catch, I'm not going to go crazy about, but you got to be a little careful about that fact. And you are approaching. You're going from 3 to 5. So you're going from 3 and then you're approaching 5 from below. Because you're going from 3, 4, 5, 3, 4, 4.9, whatever. Okay, maybe. So now you just attack it. The beautiful thing is once you rewrite the limit to take care of the infinity problem, I like that phrase, then you just attack the integral like you normally would. Now, is anybody freaked out about the integral? The inside's basically linear, so I shouldn't have to do a u sub. This is, come here. I can rewrite this as 5 minus x to the negative 1/2. Is that cool? If the inside of something is linear. Now you could do a u sub if you really want to here. You desperately don't need to. What's the integral of something to the negative 1/2? How do you integrate x to the negative 1/2? Yeah, so add 1, so it's x to the 1/2 divided by 1/2 or multiplied by the reciprocal. So it's 2x to the 1. So this would be, there's one little thing wrong with what I'm about to write down. All right? If you say, come on, Jim, what the hell, man, get it right. What's the one little thing wrong I didn't take into account?
Negative.
It's got to be a negative outside because there would be a negative that comes out when I take its derivative, right? So, I mean, if you're able to handle that, the interior is linear. I just have a -1 coefficient that has to be taken care of. If there was a 2, I would have had to have been over 2 to take care of that. Or you could just use u sub here if you really want to. That's fine. U equals this, du equals negative dx. That's where the negative comes from. Either way. And now this is from 3 to t. So what do you get when you plug that stuff in there? -2 square root of 5 minus t. Is that cool? Right? Just plug a t in. Minus negative, so plus 2 square root of. Good. Plug a 3 in. 5 minus 3 is 2. What happens when t goes to 5 from below here? What happens when I let t go to 5? 0. Beautiful. Kick ass. So that piece goes away. 2 root 2 done. So, let me give you this handout. I want you guys to look over it. I've got both situations explained, and then I got a problem that deals with both situations. I want you guys to work on it alone or together. Totally up to you.